All right, so I want to take a little time to stop and think about things that you need to know and remember to solve these problems. Because spring dynamics actually is going to be easier for most people than rotation. But there's a few things that you have to keep in mind, because if you forget some of these items, there's very, very common mistakes that will cost you lots of points. So the first thing to remember is that the spring force is always in the opposite direction to the displacement. So if you displace an object to the right, then the spring force is going to act towards the left. You don't have to include the negative sign every time you use Hooke's law. You can treat it as a magnitude and then apply the opposite, like when you write a net force equation. So if you have already defined the spring force as being left and called that negative because there was a push force going right, then you've already accounted for the negative. Don't put it in there twice. So that's something to be careful of. The next thing is to remember that the spring force is not constant throughout the motion. Because your spring force is proportional to displacement, the further you displace it, either by stretching or compressing, the bigger and bigger the spring force is going to get. So that's going to affect every instant in time. So the spring force is not constant throughout the motion, unlike something like with the gravitational force or the friction force, that's going to be constant as long as you don't say change like the mass or the coefficient or something along those lines. You cannot, absolutely cannot use kinematic equation while an object is being acted on by the spring force. Now, we're going to do a problem with like a train pulling a spring, and the train itself was going at a constant speed. So therefore, whatever force is driving the train is equal to the spring force. But that doesn't mean that the force that the train is exerting is constant all times. It just means that they were always equal. So you cannot use the kinematic equations, because if your spring force is constantly changing, then generally that means that your acceleration is going to be changing. And in order to use the kinematic equations, you have to have a constant acceleration. So that's one thing to keep in mind, is the kinematic equations are not your friend in this unit. Now, that doesn't mean that if you, say, like launch a spring off of a table, you know, so I've got a block here and I launch it so that the block falls through the air and hits the ground. Once it leaves the spring, then you can use the kinematic equations. But let's say that the spring's original length is here. So I've compressed the block so that I can then let it go and so it launches it, that I cannot use the kinematic equations in this region right here. But at the point where basically the spring force would be zero, because the spring is neither stretched or unstretched at that point, from there on I could use kinematic equations. Additionally, energy changes with the springs are non-linear, because the spring force is proportional to displacement squared. So that means if I double the displacement, I'm going to get 4 times the change in potential energy. If you're dealing with a conservative situation, then any gain of potential energy causes a loss in kinetic energy, and so your kinetic energy would behave the opposite of the spring force. The spring force is a conservative force. So that means energy is going to be conserved, as long as you don't have any other non-conservative forces, such as friction or like an external pushing force, something that would be non-conservative. So just as long as you have like a frictionless surface, and I have a spring and it's moving back and forth on the spring, I'm going to have conservation of energy. And then we always define our spring force to be 0 at the unstretched length of the spring. And that also means that the elastic potential energy is 0 at the unstretched length of the spring, because that's when your displacement is 0. So anytime you're doing energy conservation, we generally define potential energy to be 0 wherever the unstretched length of the spring is. And that's going to often include when there is gravitational potential energy. And that'll matter with things like vertical spring systems. So what are our options for solving problems then, based on those things we have to remember? So we essentially have 2 new things that we've introduced. We've introduced spring force and elastic potential energy. So generally the dynamics method would involve setting up net force equations. So I can use dynamics generally to find like an acceleration or a missing force at an instant in time. You can also find the displacement at an instant in time. So if you're using the dynamics method, they're generally not going to give you information about speed unless it's a constant speed. Because we're just going to be looking at the net force equations. We cannot use dynamics in this acceleration to relate to find a speed, because this acceleration, at least right now, when we learn about simple harmonic motion for oscillating spring systems, we'll be able to do a little more with speed and acceleration. But for right now, we really can't find speed using just a pure dynamics method, because kinematics does not apply. So then we do have an energy method. So if we are looking for speeds or displacements, and we're looking at two different instants in time, so for example, a starting time and a later time, then that's really where the energy comes from. And I would generally start by drawing a work energy diagram like we did in our conservation of energy unit, because you will see situations starting now that could involve elastic potential energy, gravitational potential energy, rotational kinetic energy, translational kinetic energy. So we have a lot more things that are possible with these energy diagrams. And they'll like to do situations where maybe an object is, say, swinging on a pendulum type idea, and then maybe they cut the string, and then the ball falls and it hits a cart, and then that cart starts moving with the ball in it, and then it collides with a spring. Or you start off on a ramp and the ball rolls down a ramp, it hits, collides with a spring. Who knows what other types of things are going on in those situations. But with the work energy theorem, you can use it just to transfer between kinetic and potential energy, or you could even go and then find the spring force, because the spring force is going to do work. But you just have to remember that when you're doing work energy, your work, remember, if I have a force displacement graph for our situations, our area is not a rectangle. So your work is going to always have to be found with the area under the curve, which we talked about a little bit earlier. You cannot use work does not equal F times D if there's a spring involved. Now, if this force is constant, it's some external force, it's constant, you're trying to find the work done by that external force, that might be different. But if this force is the spring force, this equation is completely invalid, and I see people use it all the time. So those are your different options for solving problems. So we've already, already seen some problems involving the spring force and net force equations in the spring force example problems. You're going to see some more types of problems in the spring dynamics example problems, and then in your homework assignment.